That part is clear. But how reliable this number is? Is this by chance, or is it real? Is it really there? The correlation is really there. That's what we are trying to do the test. The null hypothesis is, is actually stating that to do the test and to make sure that this number is reliable, we need to do hypothesis test or inferential statistical test. What is that is, we are taking null hypothesis situation as true. Right? Null hypothesis situation true means no correlation. If you say no correlation, I'll shuffle the data and try to calculate correlation. I should get this number very frequently. Then I accept null hypothesis. Did you get that point?
Yeah.
When null hypothesis situation is there, whatever the order we have here is not important. That's what indirectly it is saying. It is saying there is no relationship. Whatever you say, whatever you propose, 0.87 is not real. It is actually by chance, we are saying. If it is by chance, right, when you shuffle also it should happen. If it is by chance, when you shuffle data also it should happen, right? When you shuffle data it will happen. How frequently it is happening? If it is very frequently happening, p-value is going to be high. And null hypothesis situation, how many times this same score occurred out of 100? That is the probability value. Did you get that? In null hypothesis situation, out of 100 times, when you try to calculate correlation, how many times you got this 0.87? That is the p-value. Did you get it?
Yes, sir.
In null hypothesis situation, how many times out of 100 times you calculate the correlation? How do you calculate 100 times correlation? You shuffle the subject to calculate correlation, subject to correlation, subject to correlation. Like that you calculated 100 times. Out of 100 times, how many times you got 87.87? If you get it many times, when I say many, how many? The alpha threshold level is the how many thing, which decides whether you have to accept null hypothesis or reject null hypothesis. Okay, or is this correlation by chance or not will be decided by the alpha, the threshold. Out of 100 times, if the 0.87 happens even 5 times or 6 times, I'll accept null hypothesis. Say that this is by chance. Got it? This may not be right here, but that alpha level you should change. Maybe 20 times. Out of 100, if 20 times this is coming, then I accept null hypothesis. If I say that, right, the p-value, if it is greater than 0.2, we accept. Less than 0.2, we reject. Got it?
Yes, sir.
Clear, right? So that what is p-value? If you understand, right, this whole thing is clear. What is p-value? The probability of getting this number when null hypothesis is true. The probability of getting this number when null hypothesis is true. The probability of getting this number when null hypothesis is true. That point you need to remember. What is null hypothesis? It is by chance. This number, whatever you got, is by chance, or this is not real. When I say this is not real, even when I shuffle it, it should happen. Right? I'm challenging you, right? You said no, it is not real. So I will shuffle the data. Show me how many times it is happening. It is happening very rarely. That means it is real. Got it, right? So that's what I actually tried to do it here. See this? I am sampling subject 2 and resetting the index. When I sample the subject 2, right, the data gets shuffled, but indexes will not change. When you reset the index, right, the indexes will become 0 to 1. So 0 index will be correlated with 0 index, 1 index will be correlated with 1 index. So these values shuffle, really shuffle. And then I am actually calculating correlation. When I did that correlation, right, let me try to run that. So very rarely I was getting 0.87. That's where the p-value is too far. The z-score for this 0.87 or t-score for this 0.87 is very small. Based on that number, sorry, very big. Either it is negative or positive, it is very big, very big. Let me try to explain that also in a. Rest of you guys, did you get it or are you getting it now? Is this a useful, session or am I actually wasting time?
No, Rama, it's very useful for sure.
I actually saved it yesterday, right? So here, right? So let me take a screenshot and explain that concept. So rat example is very important. Rat example is the basis for all these whatever things we are learning right now. Okay. So even in chi-square test and ANOVA also we'll see p-value. You need to understand what is p-value. Okay. So let me take a screenshot. So when I'm talking, right, I'm making many statements. You may not understand. You should stop, right? What is that? No, I didn't get it. So it is not your problem. When I'm explaining inferential statistics or machine learning, it is not your problem. It's my problem. When I explain, I may be in an impression that you already know, and I may be going in a faster pace, or somebody would have answered it, and I thought, you got it, and I'm going in a fast. So you should stop and ask. Okay. So here, this p-value is the probability of getting this number when null hypothesis is true. What is null hypothesis? Even if you shuffle, you get this number many times. It is not so significant. Whatever relationship you see between these two sequences is not real. Okay. So when I say the p-value, right, what am I doing? I am going to calculate the z-score or t-score for this number. When I have to calculate z-score or t-score, what should I have? I should have many numbers, right? Many of these numbers. How will I get those numbers like this? I sample subject to do correlation test. Why am I doing sample? Because null hypothesis situation is true. When null hypothesis situation is true, this order doesn't make any sense. When null hypothesis situation is true, this order is not significant. The relationship is not significant. Indirectly, we are saying this order is not significant. Do you agree? The relationship is not significant means the order in which the sequence of data is, you can shuffle both also. You can shuffle both and do test also. Okay. The order is not significant. So when I say order is not significant, I am shuffling and testing correlation, shuffling, testing correlation, shuffling, testing correlation. If I do 10,000 times of this test, this code execution, I'll get 10,000 numbers. Do you agree? Are they similar to this number? The numbers I am getting when I do shuffle and test, shuffle and execute this code, are those numbers are like this number or not?
They should be same if hypothesis is true.
Yeah, null hypothesis is true, they should be same, right? Basically, we are calculating correlation here. Here also correlation. They are all correlations only between these two data. But this is with the original data. This is shuffled data. Why are you shuffling? Null hypothesis, true situation you took. So we got many numbers there. When you have many numbers, right, there will be a sigma, there will be a mu, there will be a sigma. There will be a mean and there will be a standard deviation. Using mean and standard deviation, you can calculate this number's z-score. Right? What is z-score? Z-score is equal to x minus mu 0.8735 whatever minus mu divided by sigma. That number, right? When you actually do many experiments, 10,000 experiments you do, it will definitely be a normal distribution. Central limit theorem. It is not a mean, but generally when you do too many experiments, right, on something, generally it tends to reach a normal distribution. Maybe 10,000 or 100,000 if you do, it will definitely reach normal distribution. When I say normal distribution, there will be some correlations, right, which are occurring too many times, number of times on y-axis, or probability, doesn't matter. Right? When you do too many times, some are happening a little less, some are happening even lesser. So this number is occurring very far, maybe on the positive side, because the positive or negative, it doesn't matter. Maybe it's happening on the positive side only, because when you shuffle, right, these numbers are coming negative, right? So 87 may be happening somewhere here within 3 standard deviation, right? If it is beyond 3 standard deviation, we have got 0.15, 0.015 as p-value, right? In the rat example, we got p-value as 0.015 because 99.37% of the times it was not happening. Okay, but here the p-value is 0.000060 and then 49, 55, 49055 whatever. So that means it is happening very far, maybe 10 standard deviations away or so. Okay, so in normal hypothesis situation, when hypothesis situation is true, this number is occurring very rare. That means this is not by chance. If it is by chance, it would have happened when you actually shuffled the data. When you shuffle the data, it is happening many times. That means it is by chance. One of those shufflings actually gave you the score, but it is not significant. So when you calculate the correlation coefficient, you want to make sure it is real. You need to do the Pearson test. You don't care. You just wanted to look at the correlation test. You can use, series or data frame. We have that method, right? CORR. You can use that. Generally, we'll use CORR only. I am taking this much time in explaining because I want your statistical concepts to be solidified. Okay, because I know and I am explaining. If I don't know, right, I would have skipped very quick. Okay. So any questions? Now you got it?
Oh, yes, sir.
So on x-axis, what we took in this graph, in this normal distribution plot?
Correlation coefficient.
Yes, correlation coefficients calculated when null hypothesis is true. Many correlation coefficients. Good, sir. Thank you.
So basically, considering the null hypothesis is true, and then we do calculate with shuffling lots of correlation coefficients, and then for this particular value, when you calculate how much deviation from the number of standard deviations, then we'll get the p-value.
Probability, right? I think you forgot that that concept. I will just remind you that. See this here. We actually anytime the hypothesis testing is done like this only. When null hypothesis is true, right? The environment in which the null hypothesis is true. If I say something, if you say it is not true, I'll say let us do it. Whatever you say is true, we'll do it. That's what is the the inferential statistic or the hypothesis testing is all about. Right here, this guy said that drug is actually affecting. The people said no, your drug is not significant. Okay, let's do the test, right? When null hypothesis is true, we took mean, we calculated standard deviation and looked at this number 1.05 significant, that response time, how frequently it was happening when null hypothesis was true, right? It was not happening 99.7% of the time. That means it is happening only 0.3% of the times. That means 0.003. Now it is one side if you take 0.0015 or 0.15, the p-value, right? So 0.0015 is the p-value. How that's by taking the probability we calculate. That's probability only, right? How frequently it is happening when null hypothesis is true. That's the p-value. How frequently the expected result or outcome of the current experiment is happening when null hypothesis is true. Okay, so same thing we did here also. Now this guy said that Pearson said that it is not significant, and then he took the data and shuffled it and then calculated the many correlation coefficients. When you have many correlation coefficients, you will have mean, you will have standard deviation, it will be normal distribution, and you can find out the p-value also, how far it is. Right? The 3 sigma rule actually says that within 3 standard deviations, 99 point. So if this number is falling, how do you know? The z-score you need to calculate. For this number, you need to calculate z-score. If you look at this, we calculated z-score for this number. 0.015 z-score is what? It is that, I think somewhere. I didn't calculate it, I think. Yeah, I didn't put it in the paper, but the z-score is what is actually showing you that z-score is 3 here. Right? So when it is 3 standard deviations away, we already know the sigma rule, 3 sigma rule. Where is that? Using this 3 sigma rule, we calculate the probability. Area under the curve is 1. From here till here, it is 99.37. So beyond it is 3. That's how we calculate it. Right? Same thing will be done internally when you say Pearson R. Okay.
Yeah, the confusion I had was regarding the calculation of the probability. There will be lots of shuffling done on the parameter 2, and based on that, lots of correlation coefficients will be derived, and this particular probability of without shuffling, whatever this is there, what is the probability? I think that was what I missed, sir. Now it's clear.
Good. So this is actually calculated with original data and kept aside. And then this number will be found out. The p-value will be found out by doing this shuffling and finding mu and sigma and how far this number is in that distribution.
Yes. So when we execute that line of code, is it internally shuffling and?
Yeah, it is doing it internally. The hypothesis testing is done. Without doing hypothesis testing, you will not get this p-value. We can do that. If you actually do maybe 10,000 iterations and capture all those things into a list, and then you can calculate mu and sigma and see how far this is also. You can do that.
Yeah, that we are actually doing, to understand. Right. So, but when this line 34 is executed,
internally it will do.
Internally, how many samples it is, or how many times?
I don't know. Maybe we need to look into the API. I don't know.
Okay, understood. So that was one of my question also. Like, is it internally doing all those repetitions?
It will. See, in AI, right? I'll be explaining many concepts, but the implementation is already there. You no need to worry about the implementation, but you need to know how it is happening. Right? If you see, right, I can explain you like this also. You looked at this number. You look at this number. If it is less than 0.05, this is real. If it is more than 0.05, rather than or equal to 0.05, this is not real. That one statement is enough, right? But you don't know why. Why this p-value? What is that significance? You don't know that. That's what we are trying to understand the complete theory behind it. It will do it internally. Maybe 10,000 iterations it will do.
Yeah.
Okay. Good, right? Everybody is good. I think p-value you got more clarity now.
Actually, I have some other questions.
Please.
So in the linear regression problem, so we learned that this p-value is calculated based on the individual features. Maybe I'm asking this question early, but is this that there is no p-value concept if we are going for the multiple LR problem?
When you don't use this statistical method, this is a statistical method. This OLS is a statistical method.
Yeah.
You don't use statistical method, right? This p-value will not be there. We will get when you. Okay, let me explain this way. So this OLS algorithm is a statistical approach where it actually tries to check whether individual feature is important or not by doing the hypothesis testing. That's where you got p-values here. Okay. There is another algorithm for linear regression. This is linear regression only. OLS is a linear regression only. There is another algorithm for linear regression in scikit-learn. We'll see that. We will use scikit-learn only. This is just for, just to make your statistical concepts solidified. I am taking these examples and explaining. From next week onwards, we will never touch these. Okay? Promise. I promise. And you don't need to be confused also. The next approach is going to be linear regression algorithm. From let me show you the site. This is the algorithm. Okay, this algorithm uses linear algebra. There is a linear algebraic calculation, right? I said that all the equations will be solved at once and all that. It uses linear algebra, and you will not have any p-values or anything else. There is another variant for the linear regression. I SGD regressor. No, SGD regressor and linear regression both are from scikit-learn, and this is more prominent or more important when compared to other. This will use an algorithm called as a solver called as gradient descent, which will not even use linear regression. It will use calculus. Linear regression is linear algebra will be there, but the major part in this algorithm is going to be calculus. I'll explain. All the linear algebra, calculus, everything. You no need to revise all that big books. It is just a simple concept of derivative. I'll explain that. Got it? So p-value is not going to be there forever. We are just trying to understand the statistical concepts, inferential statistics, and how exactly it is working, and how the statisticians were able to do these predictions or feature importances historically. We have seen when you look at SGD classifier, SGD regressor or classifier, right? There will be a concept called as regularization, which actually tries to find out the important features. That is purely mathematical approach. No p-value, no statistics, because statistics is all about approximation. There is no guarantee. Right? There is no guarantee, because now if you look at correlation coefficient, I said that this number is not guaranteed when the relationship is non-linear, right? If you look at this theory, I said that correlation coefficient will explain only linear relationship. When it is non-linear, the coefficient will be very small, or you cannot rely on that. Anyway, you have to look into the graph. And then correlation is not causation. Sometimes there may be relationship in terms of correlation coefficient, but in business point of view, there may not be any relationship. We have seen number of firefighters and casualties, right? This may look like there is relationship, but this is not real. When you do data analysis, right, you find some features like this. You may have to check with business analyst whether this is true or not. Whatever I am seeing statistically, is that true or not? We need to check. Okay, and the other thing is, if you do statistical test, the inferential statistical test, right? Sometimes you may know the p-value may be a big number that actually shows you that that is not real. Whatever you see is not real. Got it? So in data analysis, whatever concepts you are learning is very, very important and very useful. 80% or 70% of your project is going to be analysis and cleanup only.
Yes. So this analysis actually we did on the scatter plots, the regression analysis we did, and the correlation coefficient calculation is we said as a bivariate. So does the scattered plots in the regression analysis is also a bivariate analysis?
Yeah, definitely, because when you have to put a dot on a graph, right? You need x and y two coordinates, right?
Yeah.
Childhood, right? When we were in 9th class, 8th class, we did it. Those graphs. Take the graph and do those dots and lines and all that. So you definitely have to have two numbers. But to do a bar chart or histogram, you need count and the number.
So we need only we have only one variable vector, and we are actually trying calculating the counts.
Counts are ranges, right? Ranges. Histogram actually takes ranges and.
So that analysis can we say as the univariate analysis?
Yes, it is univariate. This is bivariate. Yes.
Okay.
In bivariate, we have all these different types, right? Correlation coefficient, chi-square, ANOVA. These three are the three different bivariate tests. When you are doing bivariate analysis between numerical and numerical, we use correlation. It is categorical and categorical, we use chi-square. When you do categorical and quantitative, we say it is ANOVA. There are different approaches and different things there. Got it?
Collapsing, we said maybe it's early, but what is that meaning of collapsing?
Collapsing is very simple. If you have a numerical column, suppose that there is a age column, okay, and you wanted to you are actually trying to analyze health situation of people, right? So generally, infants will have a different kind of health situation, and the people from maybe 10 to 20 or 10 to maybe 18 teenage is going to have a different kind of health situation, and from 20s to maybe 35 people will have different health situation. 35 to maybe 50 there will be different, and 50 to 50 and above will have different. So you can actually make it into 4 groups or 5 groups, right? So the age column you can make it into 5 groups: infant group, teenage group, young group, and middle age, and old, like that. Right? So you took the numerical column and you converted it into categorical, right? 5 categories you.
Okay.
That is called as collapsing. So when you have to analyze, understand relationship between quantitative and categorical, this quantitative column will be collapsed and made it as a categorical column. We are converting quantitative column into categorical, and then anyway the target variable is categorical, so we are doing chi-square test. So I'll actually show you the examples also. Okay.
One more question on this. If we say if the input is categorical and the output is quantitative, so this is actually bivariant, and we have only two things: one is input, one is output. So if it is multivariant, then this won't apply, right?
Multivariate, I'll explain. Multivariate analysis. Multivariate analysis will be done using algorithms.
Okay.
We will actually take linear regression algorithm and then build a model, make predictions. Using the prediction and the actual values, or using the prediction and the errors, we will try to understand the relationship between. When you say multivariate analysis, right? All input variables together, how they are related with the target variable. That is multi. So individually one column, how it is actually spread, and what is the distribution and how data behavior is. That is univariate. How two columns are related is bivariate. Whether it can be input, both are input, or one is input, one is output. It doesn't matter. Two columns, how they are related. The third one is multivariate analysis. How all input variables are related to the target variable all together. If you look at p-value, it is always independent, right? Individual, right? Individual input and individual output. Individual input. If you have 10 features, you will do first feature to target, second feature to target, third feature to target, like that. You ignore the other features and try to do the relationship analysis. But when you are using 10 columns together, there will be an interaction effect, we call it as. One feature will affect the other feature to improve the accuracy or reduce the accuracy. We don't know which way it is actually affecting, right? So when you use all 10 columns together, how they are actually affecting the prediction should also be analyzed. That is multivariate analysis. We'll see that in regression analysis class. We'll see there is a concept called as linear regression assumptions and regression analysis. There is a whole lot of, I think I'll take around 2-3 hours of session there, and these all concepts are useful there. Whatever we see here is all going to be useful. And if you understand that, right, even when a statistician is doing interview, you will be able to handle it comfortably, whatever you are learning right now. Generally, rarely it will happen. Generally, it will not happen. Rarely, statisticians will do data science or AI interviews, because companies are thinking that statisticians can lead the AI team. That is a mistake. Statisticians can be testers, good testers for AI modules. Okay. Are we good?
In the linear regression,
Yeah.
so we have actually calculated the p-value for the intercept and p-value for the experience. So when we say the p-value is more than 0.5% for intercept, we reject, right? What does actually it mean that
intercept is not needed? Even if you take out intercept, right? While building model, you can say intercept true or intercept false. There will be a parameter to be either to keep the intercept or not, avoid the intercept. We can say, if the p-value is coming big, right? You can say intercept is equal to false. That means what is, if you look at this graph, right? This line, even if it goes through origin, that's working fine. When it is not going through origin, right, it is actually creating problem. Got it?
Yes, yes.
So if you see this here, I used more two columns, so I got the p-values 3. And when I added this new column, it actually distracted the intercept also. It actually made the intercept inaccurate or inappropriate column because of adding this column, right? We know that when we don't add this, we are getting the p-value, small p-value here. When we added it, we can see the difference. But in general, right, you may take 100 columns and try to build a model. You don't know which one is important, which one is not. So you can use p-values to do the feature selection. The biggest p-value, you remove the column, build a model. Again, the next biggest, remove, build a model. Next biggest, remove, build a model. That's called as backward selection. Okay, so we will not use these because these are not very appropriate approaches. We'll use regularization techniques to do feature selection. Okay, feature selection and feature engineering are two concepts in AI. Feature selection is whatever I am talking right now. Which feature is important, which feature is not important. That is feature selection. Feature engineering is you actually try to merge features, or try to avoid features, or try to derive some value from a feature. Those are called as feature engineering. We'll see that example. Okay. So anyway, right, I said that I'm going to take class today till 8:30 only. I joined late and we're actually discussing. Any other questions, concerns we should handle? Maybe, from the beginning. If somebody joined late, maybe Seshiram, right, you want to know something from the beginning of the classes, I can explain now.
Sir, one question, sir.
Yeah.
In the current relation problem, what we discussed when I asked the doubt. So our as per the null hypothesis, they are it is both the columns are not related. In that case, our expectation was we get some correlation coefficient as per if null hypothesis is true. We get the same correlation coefficient even if we shuffle. That's what we assumed. So can you
we are not
know?
assuming, basically we are not assuming, sir. One point there is, I said they are related. In this sequence, they are related, I said. You said the sequence is not important and they are not related. You said they are not related. Whatever you see is not true, you said. When you say whatever I see is not true, what that means? I can change the values here and then, do the relation. We are not assuming. The null hypothesis is true. That situation we are creating by shuffling one column.
No, I think I did not complete my question, sir.
Please, sorry.
So we got correlation coefficient as 0.87 or whatever it is. So we were actually looking at even after we shuffle, we get the same correlation coefficient or maybe high probability of getting the.
How many times we get? Let me try to do this. For I, for dash in range of. Let me try to do this. Anyway, we are not doing anything, right? Let me take a list and then do whatever the hypothesis testing it is doing. I'll do it here. Okay. So your question is completed, right? Did I stop you in between? Grigor.
Yeah, complete cheyaledu inka. I did not complete.
Please, sir. Sorry, please.
Yeah.
Please,
so we were looking at even if we shuffle, there is high probability or at least whatever 0.05 probability of getting the same 8.87. Then basically null hypothesis is correct. That's what we are looking at. So I just want to know, let's say if they are not related, why do we get maybe probability of or maybe 0.87 same correlation coefficient? Why do we get it?
That I showed you here. See this here? When data is like this, right? If you see this data, even if it is related or not, doesn't matter, right? Because the variance is all kind of zero, right? Suppose that this is input feature, this is output feature. There is no variance here and here or here, right? Not much variance there, right? When you shuffle or whatever, do you calculate correlation? It shows correlation, but that is not significant. There is no significance there. The relations, there is no significance. When the values are different and then relationship is there, the variance is there and the relationship is there, then it is significant, right?
Sure.
So that's what we are trying to see. Is it like this column? These columns are not. That is one thing we are trying to look at. That is one of the things we are trying to look at. Okay, so let me show you this. This is how I think you got this point. I think we are actually we have got these, right. So let me try to do a create a series object. That I said that, you know, when you do many times this null hypothesis true situation thing, you will get a normal distribution. Did you get it? Did you get it?
Yes, sir. Yes.
See, you know, when you look at this, you know, we can calculate the mean and standard deviation of these, right? So let me calculate mean and standard deviation. This is mean. Standard deviation, right? Now, if I have to calculate a t score or z score, right? Z score of what? This number, right? When null hypothesis is true, I am trying to calculate z score of this number. I think this notes is very important. Whatever I am doing right now. X minus mu, right? X minus mu is mean divided by sigma. This one. Sorry, 3.84. Right? If you say 3 standard deviations away, 99.7% of the times this number is not happening. Right? When null hypothesis is true, when you shuffle it.
Correct.
That means, you know, you can calculate p-value probability now because you know the curve, and 4 standard deviations also there is some number, you know, in that. I think 4 standard deviations. Let me see. Theoretically, I know. I am actually doing it right away in front of you. Whatever theory I know, I am actually proving myself. Not exactly explaining you, but you know, I am actually proving myself. So.
Yeah, it is clear now, sir. Yeah, clear.
See, minus 4 standard deviation 0.13. 0.13 is the minus 4 standard deviations, right? So like that, you know, when you look at these numbers, right, you can calculate.
Sure.
Okay. So that's it for today, and you know.